Our first group is now complete, and we're going to be switching over to our next student finalist of Elisabeth Millington out of Rice University. And as I do it live on navigating slides.
Thank you. So today I'm going to be presenting my paper about a comps-based approach for interpreting tree-based predictions with a specific application to the NFL draft. First, I want to talk a little bit about the motivation behind this paper. Machine learning models are becoming more and more common in sports. The issue with machine learning models is that they're not super interpretable. Like the predictions, it's pretty difficult to tell where the predictions are coming from. And interpretability is crucial, especially in sports, because it allows you to have trust and confidence in your prediction. And so with this, we propose a methodology for creating a similarity score that functions as a quantifiable player comp and therefore adds interpretability to these predictions. First, I want to talk about the existing relationship between k-nearest neighbors and random forest. Random forest models can be seen as an adaptive nearest neighbor model, where each tree in the random forest defines a neighborhood of similar players, where the neighborhoods are defined by the tree structure rather than the distance like they would be in an adaptive nearest neighbor model. And the training observations that share a leaf node with X in tree B are considered X's neighbors. And so ultimately, the random forest prediction ends up being a weighted average of the training outcomes. So from this, we are able to create a formula for a similarity score that tells us the similarity percentage between a training player and a testing player. And so W ends up being the similarity score between the query point, which is the testing player, and the training point, which is the training player. And in this application, we can frame this similarity score as a numerical player comp. So here I have linked my GitHub for the R package that we created with this project. It extracts similarity scores from any random forest. It doesn't have to be a sports application. If you want to scan the QR code, you can access the package. So now I'm going to talk a little bit about the data that we used. Our model is trying to predict how college quarterbacks perform in the NFL. So the inclusion criteria was that each player must have played in the Division I football bowl subdivision between 2001 and 2023. They must have played more than 6 games in their career and attempted more than 5 passes per season. After everything was said and done, we had a total of 2,099 quarterbacks, and each player season includes data for team, conference, strength of schedule, passing statistics, rushing statistics, and award statistics. And all of this data was publicly available from Sports Reference. The NFL data is also publicly available from Sports Reference. We decided to use ESPN total quarterback rating as our response variable because it's an EPA-based variable that is scaled from 0 to 100, which therefore allows us to include quarterbacks who are not who never played in the NFL and assign them a value of 0. We also got the passing attempts for each season. The data was very right skewed. As I said previously, we had 2,099 quarterbacks in the college data set. However, 91% of those quarterbacks never played a game in the NFL. Therefore, they had a QBR of 0. And additionally, some players put up high QBR numbers with a small sample size. For example, a backup player may have gone in for 1 game and had a QBR of 80 and then never played another game in the NFL, and that means their career QBR per season is 80. And so to combat that, we regressed QBR per season to 0 based on the passing attempts per season. And so as I said previously, our response variable was regressed QBR, with the predictors being the college team, passing, rushing, and award statistics. The award statistics and the team statistics were from the final season, whereas the rushing and passing statistics were from their an average over their college career. It's also important to note that for the college statistics, if a player played D3, D2, or in the FCS subdivision, then those stats are not included in their career stats for this model. We use the Ranger R package, which is a faster implementation of random forest, and we use the Tune Ranger package for the hyperparameter tuning. With a 70-30% training and testing split and 1,000 decision trees, we found that the ideal number of variables at each node was 5, and the ideal minimum node size was 73, with a test root mean square error of 8.61, and a little bit under half of the variance was explained. So right here, unfortunately, it looks like it is a little bit blurry, but we have the variable importance from our model. We can see that final Heisman voting is the most important variable when it comes to predicting NFL success. And then after that, it is passing statistics and then strength of schedule. It is important to note with this that a lot of the passing statistics were pretty heavily correlated with each other. And so in the future, that's something that we want to consider whenever we're building a model like this. But ultimately, our goal in this was not to create the best model. It was to create a way to interpret the model. So we spent time on the model, but not a ton of time, if that makes sense. And so now I want to talk about a case study from this model is Shedeur Sanders from the 2025 NFL Draft. Because I think this is a really good example of why sometimes statistics and predicting is not perfect, because you can't include certain like leadership or personality values that teams really care about. And so Shedeur Sanders was predicted to have the third highest value behind Cam Ward and Dylan Gabriel. But ultimately he ended up being the 6th quarterback taken in the draft. And now I can't say why that was, but also there were definitely other variables at play besides just his college statistics. We also didn't include combine performance in our model, so that also probably contributed to why he ended up not performing, but being selected lower than he was predicted. So here is a table of the player comps for the top 4 prospects from this year's draft class. As you can see, the percentages themselves are pretty low. Like the highest is Johnny Manziel for Cam Ward, and he's 2.3%. So there's not one individual that is contributing like significantly to one person's prediction. It is a combination of these, it's a combination of the players. And you can see that both Dylan Gabriel and Shedeur Sanders had their top comp was Mason Rudolph, which I thought was kind of interesting. But this just kind of is a visualization of what like the similarity score looks like whenever you're applying it to the NFL draft and using it as a numerical player comp. So in conclusion, this methodology allows for the interpretation of random forest models in addition to providing a similarity measure. It's not limited to quarterbacks, to football, or even to sports. It can be applied to any type of random forest model. It also, our application to the NFL draft kind of shows some of the limitations of statistical forecasting when you're scouting draft prospects. It's pretty difficult to model like values that teams care a lot about, like interactions with players and leadership, and just overall personality and any character issues that someone might have. For the future, we might want to do 2 models where the first model is a model that predicts whether or not the player will have a 0 QBR in the NFL. And then after that, create a model that predicts create a model that predicts the QBR if they're predicted to have a QBR, since the data was so far skewed. This also allows, I didn't say this earlier, but a lot of the predictions were really conservative whenever it came to predicting QBR. There were, I think this year, there were none that were over 40. And I think in the overall data set that we tested, there were maybe 2 players that had a predicted QBR value that was over 40. And so additionally, future direction could extend this methodology to other tree-based regression and classification models, such as gradient boosting. Thank you, guys.
Kenny Pickett or Mason Rudolph are your top comps. I think that's a stay away. All right. Do we any questions for Elisabeth? I see hands all the way in the back. Oh no. Yeah.
Hey, how's it going? I thought it was a great presentation. Did have a question on the correlated features. So the number one was Heisman finalist. How much of that do you think is a self-fulfilling prophecy? For instance, if someone's a Heisman finalist, maybe they'll be drafted a little earlier than they normally would be. And if they're drafted a little earlier, maybe they get a start. Yeah.
I think that's a really good question. I think that maybe like the finalists in the Heisman vote tend to be, I agree, they tend to be the players that are taken earlier in the draft, and which typically indicates that you're going to have a better performance in the NFL. Or I guess it doesn't typically indicate that you're going to have a better performance, but you're expected to have a better performance. So I think that is a good point and definitely something that I would want to look into further.
Question in the room, Sam, over in the overflow.
Yeah, we have two in here if there's time, but we'll start with the first one. Then you can tell me if we have time for another one.
Just one.
Mike is up there. So just
Okay. So there's some previous work in football and certainly in baseball where basically in order to increase the pool of available comparisons for calculating these similarity scores, they look at not just thinking about forecasting college to pro, but also pro to, if you think about just predicting a sequence of player statistics, then we can think of, well, it's just this year to next year. And so use things like Davenport translations in baseball to basically think about, oh, well, a player at the start of his pro career, if we can translate that to be similar, to convert that to the college baseline, then we can use also guys who are in their rookie year forecasting into their second year to do as an extra source of data to forecast guys going from their final year of college to their first year of pro. Is that something that you've looked into at all? Possibly to expand your data set some?
That is not something that we looked into before writing the paper. I think now that definitely is something that we could look into for increasing the data set, and especially with increasing the amount of available data for the NFL statistics.
Okay, let's thank Elisabeth. All right, good job.